All right, so good morning, everyone. This time is the good one. So I hope you're doing well first, and that despite all the problems of connections and also this way of teaching and studying, which is a bit particular, you are still able to make some progress. So now you should all have access to the Dropbox folder. If this is not the case, please send me an email, and then I will make sure you have access to everything. In the Dropbox folder, you have for each tutorial in particular, you have the tutorial topic, but also some articles that I would like you to read in advance, or at least to scan, so that you get a feeling of what is going on. Also, after each tutorial, I'm putting the videos inside the Dropbox folder, as I explained last time. So you can come back and study if something was not clear. Also, feel free to send me emails or comments whenever you wish. All right, so this is tutorial number 2, and today we are going to study a famous result by Pierre-Gilles de Gennes. So Pierre-Gilles de Gennes is a famous French physicist. He got the Nobel Prize in '91 for his work on polymer physics and other aspects. And he was the person really who rejuvenated the soft matter, or created even the soft matter community or field. So he was studying several things from superconductor in the hard condensed matter field towards polymer physics, weighting, liquid crystals, granular matter, biology, and so on. So he is really someone who was scanning different fields and got very important results in all these fields. Interestingly, he was then able to make connections between the various fields he was studying. And the tutorial of today is an example of that. It's a result that is making connection between polymer physics, as we will see, and hard condensed matter, and in particular magnetism. Okay, if you want spin models on a lattice, and you will see the connection hopefully at the end of this tutorial. So in terms of story, it's in the 70s. So you can see the article date here is 72. So in 71, an article by Wilson, who invented, based on Kadanoff results previously, the renormalization group theory to describe critical phenomena. Well, in 71, Wilson was sending his article for review. And Pierre-Gilles de Gennes was aware of that article. He received a version of that. And immediately he understood that there was a connection between polymer physics and this world, and he could use the tools proposed by Wilson to do some polymer physics. So quickly, in a very short amount of time, he produced this article with, as you can see, is extremely short. You have basically one page of calculations. And when I say calculation, it's really the essence of it. Each line you would need a lot of time to digest it and to make sure you're able to go to the next one. So have a look. It's a very original way of writing articles. And later on, this had implications, and people have studied and written on the implications of that result. So here, there's another article written by Tom Wheaton from the US. So this article is from 2009. So it's much more recent. And if you read it, it's very easy to read. It will explain why this result was important, despite the fact that at the beginning it was difficult to swallow. So you can have a read. You see, it's pretty long, but it's only text. And Tom Wheaton tries to explain how the result was used and what it revealed about the connections you can make in physics. So have a look at that. And today, hopefully you all have the tutorial topic now. We will try to digest that article with very simplified steps. And as you will see, there will be plenty of mathematical issues. I will, for instance, invert limits or infinite summations very coarsely without demonstration of that. And this is, of course, related to mathematical questions that I won't have time to discuss today. Also, you will see that I will take a very special limit. I will create an object, a vector, with a certain number of dimensions, for instance, a vector with 3 components, but then I will make this number of components go to 0, okay? Don't ask me what is the physics of that, because I don't really know, but this is the mathematical trick that de Gennes proposed and that allowed him to make the connection with polymer physics. So we will do some mathematics first, develop preliminary important calculations, and then we will go to a diagrammatic representation where we will try to explain the different terms that appear in the calculation and connect that to physics, and in particular polymer physics. Okay, so I hope the plan is clear. So please, everyone, take the tutorial topic with you, and I will follow the steps. Let me also switch to the whiteboard. Now you should all see my usual whiteboard. Right, if not, just tell me. Okay, so we will start very simply by describing a statistical physics problem close to an Ising problem, a spin problem, I could say. So the idea is the following. We will consider some kind of lattice. So we can represent that lattice, for instance, in 2D here, as a collection of different sides. And on each of those sides, we will place some spins. So for instance, here I will have spin number I. Here I will have spin number J. And all those spins, they are described by a vector. Okay, and you have an infinite number of nodes in the thermodynamical limit. Okay, I will say two things about dimensions. First, the space, the lattice itself, lives in a certain dimensionality. We will assume that the dimension is called D. It can be typically 3 in our usual world, but it can be a mathematical quantity that can be larger if we want. And also, we will assume that that system is placed in a thermostat at a certain temperature that is fixed for good. So D is the dimensionality of space, but that vector S, or Si, has also a certain dimension. It has a number of components, and this is not necessarily equal to the space dimension. So we will assume that vector Si has a certain number of components that I call Si1, Si2, and so on and so forth, until Sin. And n is an integer. Okay, so you could have a 10 component vector placed on a 3D lattice if you want. Okay, so this is basically what we want to have. Finally, we will branch some interaction between those spins. So they are not able to move. There is no kinetic energy. They are really fixed on a point, but they can have different orientation, like in a Ising model. Then we will branch some interaction between that spin and that spin. And this interaction will be of the type a prefactor, which has the unit of an energy, if you wish. And then, sorry about that. And then the scalar product, which is the simplest way to describe a two-body interaction. Really, you have the product of the two fields. Okay, so this is the interaction between site I and site J, and it has a certain magnitude, J, Ij, with a minus. And we want this to describe some magnetism, not antiferromagnetism. So we will assume that whatever I and J, this is a positive quantity, so that you favor alignment and not anti-alignment. All right. Finally, we will do the usual assumption that is performed in Ising models. We will assume that only nearest neighbor talk to each other. For instance, this guy will talk to this guy, or this guy, or this guy, but not after that. The interaction is sufficiently short range that you can neglect the tails, right? So we will assume that in fact, Jij is equal to either a constant for any sites for nearest neighbors and 0 otherwise. Okay? Really like the Ising model. And with all that, we are all set to start the tutorial. All right, so now it's a stat-phys problem, as you can see, and so we will go on the stat-phys problem with very basic preliminary explanations. All right, so we are starting with the first part. When you deal with such a statistical physics problem, you start with the Hamiltonian, and so the Hamiltonian is purely based on the interaction energy here. So you have minus J times the sum of all scalar product for all sites, I and J, but you assume that you sum the pairs only once. So I just used I smaller strictly than j. And also I use this notation to express that I'm summing only on the nearest neighbors. So this will be my notation to express the fact that if you jump one neighbor, there will be no interaction between the two, only nearest neighbors. All right. So this is really the potential energy of the problem. Once I have the Hamiltonian description of the problem, I can go now to the partition function as usual in StatPhys. And so the partition function will be very formally simply the integral of the Boltzmann factor. We are in a thermostat, we are in the canonical ensemble, and so basically, formally speaking, this is the definition of the partition function. So here the summation is not specified. Of course, now we have plenty of spins, and each of those spins, they have a norm, which is fixed, and we will comment on that in a minute. And there are also angles. So we will assume that the norm is fixed, so that the only degrees of freedom are on the orientation, the solid angles. So this will be expressed as the product on all solid angles, at least their element. So I'm summing on J, for instance. Let me sum on another index, K. And I will basically, so beta is 1 over KBT. So I'm just rewriting everything with a new temperature Tj that I will define in a minute. And then there will be the summation on all nearest neighbors pairs of the scalar product Sj, right? And omega I or k is the solid angle associated to one spin, and you have all the degrees of freedom that matter. So here I've made two assumptions. So first of all, I've defined Tj as basically the energy scale of the problem, so I can transform it into a temperature immediately. And the second thing I mentioned is that the norm of the S vectors is fixed. So De Gennes proposed to say, and it's a mathematical choice, you will understand it later, that the norm of any of the spins vectors is equal to n. Okay? You could decide to normalize it by 1, by a physical quantity like h bar, whatever. He decided to normalize by n. It's a choice, and it's self-consistent, at least for now. All right, so only the orientation matters. Now, another step. We would like to rewrite this partition function as a function, as an average in the uniform distribution ensemble, not the canonical ensemble. So to do so, let us divide by the integral of all the element of solid angles. So we end up with this formula, which is exactly the same as previously. Again, you have this Tj over T, the summation over nearest neighbors, and the two-body interaction. But now we divide all this term by the integral, just to normalize. All right, and I can redefine this quantity as capital omega. It's the total solid angle for the all the degrees of freedom of the problem, and so this is simply the integral of this guy. So I end up with the fact that z over omega, which is really the step here, z over omega, will be given by, let me just switch here, will be given by an average. As you can see here, we have the average of that quantity in the uniform ensemble, because we are summing all the solid angles without any specific distribution. At least the distribution is 1, if you wish. So it's the same for any solid angle. They are all equivalent. It's a purely isotropic problem here. So we end up with the average of the exponential term Tj over T with the summation on nearest neighbors. And we define notation. This is the average in the uniform ensemble. So it's simply the integral of the quantity you want over all the solid angles divided by the integral of all the solid angles. Okay, so it's really the uniform average. All right, this is really a mathematical trick for now. We are just transforming the partition function into some average, but we don't learn anything for now. All right, so now we will do something else. When you are in a canonical ensemble, you have an average, and this average is against the Boltzmann distribution, so it's different from the uniform averaging. So we will try to connect what is the canonical average in terms of the uniform average, all right? So let's take some observable, some physical observable of your problem. Let's call it G. It can be energy, it can be momentum, it can be position, whatever you wish. And the canonical average, formally speaking, as you all know, is simply, so I don't put any zero here, right? It's really the standard averaging in canonical ensemble. Well, it's simply this guy, and in a formal way, it's simply normalized by the partition function. Okay, that's what you would call an average in a physical world when you have a thermostat. All right, so as you can see from here, now we can transform that average using the zero notation. And so this is in fact the integral over all the possible solid angles. Again, this beta h g over sum the integral over all the solid angles of the Boltzmann factor. And now if I consider that I have an uniform distribution for all the solid angles, this becomes the uniform average of that product in the zero sense divided by that. So it's really a trick, and you will understand the use of that later on. But basically, we are transforming a canonical average under a certain temperature into a uniform average. But of course, we have to pay the price that now the quantity is a bit more complex. So it's just a mathematical writing for now. All right. I go slowly because I know there are less interactions by Zoom. So I want to make sure that you're all with me. Okay. If not, please interrupt. That was for the preliminary steps. Now we would like to do a part only on mathematical features. So let me now focus on the situation where I am now only in the uniform ensemble. So if you want, I'm taking the limit t goes to infinity. Because if t goes to infinity temperature, you can see from the expression here that the Boltzmann exponential will go to 1 at the bottom as well. And so you end up with the fact that G, under the canonical average will become strictly equal to G0 over 1. And the average of 1, due to the normalization that was correctly performed, is 1, so we end up with that. So in the infinite temperature limit, the averaging in the canonical ensemble is the same as the averaging in the uniform ensemble, obviously, because at infinite temperature, all the directions are equivalent. The energy doesn't mean anything anymore. All right, so we will deal now with only one spin. So we will focus on SI. And in fact, since it's only one spin alone and uniformly distributed, there is no interaction with other spins for now. And we also assume that there is no temperature and so on. We will call that spin, by definition for now, S. We drop the index. Okay, so we are dealing with one spin, okay, that is able to freely rotate in space, and all the directions are equiprobable. So we need to introduce a mathematical object for probabilities that we call the characteristic function. So the characteristic function is just the Fourier transform of your distribution, if you wish. So here, the uniform distribution. So we call it f of k, and basically it will be simply the average of the Fourier mode. So you will transform the variable, your random variable s, into a Fourier variable k. And this is in the uniform world or at infinite temperature. So we are in a zero average here, okay? Stated differently, this is simply the summation over all the solid angles. Sorry, here I have only one spin, so I will drop this product and keep d omega. And I'm integrating this guy over the integral over d omega. Okay, so this is really the transform in the Fourier sense of the uniform distribution, which is 1. And the interest of that Fourier transform of the distribution is that derivatives of it will provide all the moments of the distribution. So it's a very useful tool in probabilities to go to Fourier space. So I would like to illustrate that quickly. So f of 0, for instance, is the first moment of the distribution. We can have a look at it. It will be the integral of 1, the average of 1 in the 0 norm, so it's 1. So this one is very trivial, but it is just saying you that the distribution is correctly normalized. Okay, so f at 0 provides you the normalization. Now let's derive f. So to that I will introduce derivation operator. The alpha will be by definition the derivative in the partial sense with respect to the alpha component of the vector k. Let me just also comment on the fact that k, since it's the Fourier transform of S, as you can see here, has the same number of components, k1 towards kn. Okay, so it's also an n component vector. So now let me take the alpha of f, and so this is the alpha of the definition in the uniform ensemble. And so if I derive with respect to k alpha, s alpha is jumping in front, so I have I s alpha exponential I ks, which is again in the uniform ensemble. And therefore, if now I take d alpha evaluated at 0 and not at any vector k, I end up with I s alpha in average in the uniform ensemble. All right, so you immediately see the implication. It's the moment of the distribution, the first moment of the distribution, which is the average of the random variable s for the component alpha, is simply provided by, apart from a prefactor, a certain derivative of the characteristic function. So the characteristic function contains the first moment. All right, so we can go on and now do the same thing, but with next order derivatives. So let me, for instance, take the second derivative with respect to alpha and then beta, or the reverse. Well, then I will end up with, as you can see in the definition, I will have I s alpha and I s beta that jumps. So you have a minus s alpha s beta, and then again I k s. Oops, sorry. And of course I was deriving f. So now the same thing but evaluated at 0 provides me the second moment apart from a prefactor. All right, you see, so I derive once the characteristic function, I have the first moment, twice the second moment, and this is really true for the nth moment, apart from prefactors. So that is why knowing the characteristic function is the key in this problem. So I will find this characteristic function in a very special limit, as you will see in a minute. All right, so before finding f, we would like to know an equation on f, a differential equation, and this is what we would like to find now, and we will invoke the normalization for that. So let us just remind definition. So f is, as I told you, defined this way. The first derivative of f is defined this way, I s alpha exponential I k s. And the second derivative of f with respect to alpha, so I call it alpha with a square here, is the same thing with a minus s alpha squared exponential IKS in the uniform sense. Now, I would like to find the Laplacian operator, so I will just define it as the sum over all the components of the second derivative with respect to a given component. And under this definition, the Laplacian of f will be given by minus the sum over alpha of this guy. Now, averaging and summing are two linear operators. I can switch them here, and so I end up with the following result. Delta f is equal to minus the sum over alpha of s alpha squared, IKS. Now, remember that I told you that the spins have a norm, which is a constant number. It's an integer called n, right? So this is also the summation over alphas of all the components squared. So in fact, this quantity is simply n. And so it doesn't depend anymore on any orientation or so. So it's a constant number that can go outside the averaging by linearity. So delta f is equal to minus n times, well, we recognize the characteristic function here. So this leads me to write the following governing equation for f. It's a linear differential equation. All right, so I guess there are no problems with that. So once we have fixed n, we have a certain equation, and by solving it and invoking the proper boundary conditions, we might find f. And if we have f, then the problem of one spin is done because we can just derive all the moments from it. All right. So now comes the question about the dependencies of f. So we are saying from the beginning that very generally, f is a function of k. But remember that f is the Fourier transform. So if I write it as a Fourier transform, is the zero average of IKS. So it's d omega, the solid angle, is the Fourier transform normalized by d omega. And so if S is a uniformly distributed vector, as is the case now, we assume that all the orientations are equivalent. And so this property will be transferred to the Fourier world. We will also have f, which is in fact only a function of the norm of the vector k, but not the orientation. Exactly like the uniform distribution doesn't depend on the orientation, only on the norm, which is fixed. You can convince yourself by taking an example. Let's take an example in a 3D world. In 3D, it's easy to express the solid angle without having use of any gamma function. So in 3D, f of k would simply be the integral over the two angles, d theta, d phi, and with the Jacobian here. And I will have I k s and the cos theta, which is the angle between k and s. So I can always define my reference axis as the one of k, and then here there is an angle theta. All right, the integration is only on theta and phi, so I can always choose my reference axis as I wish, and I take k. In addition to that, so this is normalized by d theta, d phi, sine theta, and we know the value of that, it's 4 pi. So it's 1 over 4 pi. The integral over phi gives you a 2 pi, and then you are left with the integral over theta between 0 and pi, sine theta, and IKS. And remember that S has a norm which is square root of n, because S squared is fixed to n. So IK square root of n cos theta. All right. But you immediately see from this expression in 3D, which is the one proposed here, that it only depends on the norm k. So you know it's obvious from a uniform distribution, you get the same property in the Fourier world. All right, but this is an example in 3D. You could do that in n dimension if you wish. All right, so we have the following fact: f of k is in fact only a function, and I keep the same notation for simplicity, but I should change, is a function of only the norm. All right. So this will be helpful because we can then simplify a bit that operator. Okay, we can go to a one-dimensional world. So to do that, let's just do the change of variables in the derivative. So the derivative with respect to coordinate k alpha of f, well, is the derivative of f with respect to k. And by composition, now I need to derive k with respect to alpha. So I'm just composing the derivatives, and I will, in the following, just note things quickly, since there is only one variable, as the derivative with a prime. All right, so this is f prime d alpha k. Okay, so what is d alpha k? Well, k is the sum over all components squared with a square root, by definition of the norm. Therefore, d alpha k, oh sorry, let me just replace this alpha by beta so that there is no confusion. All right, we are summing on it, so there is no problem with that, where alpha here is one specific index. So this is 1 over 2 times the square root beta squared, and then I multiplied by 2 kb, k beta, k alpha, sorry. Up. All right, so this is simply k alpha over the norm of k. So in the line above, I end up with the following result. It's a function of k times k alpha. All right, so I've identified the first derivative of f with the knowledge that now there is only the norm that matters. Let me go to the Laplacian, so I need the second derivative. D alpha squared, so 2 times the operator derivation with respect to k alpha of f, well, is equal to d alpha of what we just wrote, f prime over k times k alpha. So then I have 2 terms. I can take the k alpha part and the k part separately. So the first term is when I derive with respect to k alpha, I end up with f prime over k. And the second part is when I keep k alpha, but I derive f prime over k with respect to k alpha. So I call it d alpha of that quantity. But previously, as you can see here, we already made a derivative with respect to alpha and transformed it into a derivative with respect to k, provided this composition term. So we do exactly the same here. This is equal to the first term plus k alpha, and instead of the d alpha derivative, I take the prime, but I multiply by d alpha k to make the composition. It was a function of k, so I do exactly the same process. All right, and we know that this guy is simply k alpha over k. So altogether, we can recombine everything into the following form. We have k alpha squared over k times f prime over k derived once more. And if I expand or explicitize this part, I end up with k alpha squared over k. And then I have 2 terms. I have f second over k plus minus All right, so yes, I'm just checking that there is no k that disappeared in the process here. All right. Perfect. All right. And then now we want to express the Laplacian operator. So the Laplacian operator, we will do it by integrating over alpha. So Laplacian of f is sum over alpha the alpha squared. And so I'm summing over alphas the two previous terms. So I have one which is f prime over k. And I have another one which is k alpha squared over k times the difference between f second over k minus f prime over k squared. All right. Here you can see that this doesn't depend on any alpha. So it seems that it can go outside the summation, and therefore we are summing over alpha. Alpha is the component index of k, so it goes between 1 and n typically. So you have n times f prime over k. The second thing we have here is, again, the alpha only is summed or appears here. So you have the sum of alpha over alpha of k alpha squared. So this is k squared. Since there is a k here, this is a simple k. So you end up with k times f second over k minus f prime over k squared, which is f second at the end, this term, plus f prime. In front, you have n minus 1, everything over k. All right, so this is delta f. And now we have to remember that the equation is delta f plus nf equals 0, if I remember correctly. Yes. And so this becomes and so we end up with the governing equation, which is the one written in the tutorial. Okay, so that is nice. From symmetries, we've reduced the problem into an ordinary differential equation, but on one variable instead of d variable, or I see here n variables. All right, so far, purely mathematical result for the uniform distribution. Now, let us close the problem by having boundary conditions. So it's a second order differential equation, so we need two boundary conditions to be able to integrate it and have a unique solution. All right, let's look at the first one, f of 0. Well, we remember that this is equal to f of 0. If I remind you that you have the vector in the definition of the characteristic function, so it is the integral of the average of 1 in the uniform ensemble, which is 1. So we have one starting point for f. Now we could take the first derivative of f, and the first derivative of f, we can remember that d alpha f, it was written, I guess, when we are looking at how a characteristic function provides you moments of the distribution. You can see, oh, sorry, it's here, that here the derivative with respect to alpha of f at 0 provides you the first moment, right? So this is what we are going to do now. It's the first moment up to, so here we have at the 0 average. All right, and now we have to remember what that means. Well, we are looking at one component of a spin, but that is uniformly distributed, meaning that this direction is equivalent to that direction. We already went to those discussions in the previous tutorial. It seems that this is as probable as this. So on average, the projection is 0. So we end up with 0. So this is for the derivative with respect to alpha, but we know that the derivative with respect to alpha of f is equal to f prime, and we were multiplying this by k alpha over k by composition. So if you want, this, since those two guys, they go to 0 in a similar fashion, this implies that f prime of 0 is equal to 0. So we have a second boundary condition, the first one being already expressed. All right, so we have our two boundary conditions. We have an equation that is linear, so a priori the coefficients are constant here. No, sorry, there is a coefficient that is not constant, but we'll come to it in a minute. And so we can integrate it. And since the whole argument about the gen from the gen is to go in the n equals 0 limit, this is called the n equals 0 theorem at the end, we want to investigate the n equals 0 case. So again, I'm only considering mathematics here. It might sound weird to have a spin with 0 component. Okay, so it's a limit that is perhaps unphysical, but I have still the right to study it in a mathematical sense. So let's look at the previous equation, but when n equals 0. So the previous equation is here. So if n equals 0, I will kill the linear term in f, and I will also simplify the first derivative here, term. So I end up with a simplified equation for the particular case where n equals 0, which is it might be a minus f prime over k, which is equal to 0, so I can rewrite it this way. See, this is the equation in the n equals 0 situation. So I can transform that into differentials. So it's the differential of f prime divided by f prime, and here I have dk over k. And so integrating that provides me 2 logs plus a constant. Okay, so f prime is equal to the Neperian logarithm, which I note log of k, plus a constant. Stated differently, I can always absorb the constant into the log, because we know the transformation of product inside the log to summation of logs. So in any case, this will be a constant that I call a times k. All right, so f prime is equal to a times k, so I know f by a second integration. F is equal to a k squared, it's a parabola, plus another constant, and let me call capital B, for instance. All right, so here is the general solution, but now I have 2 boundary conditions, so I can specify A and B priori. So f of 0 is equal to 1, and it is, from my expression here, equal to B. So this provides me the fact that this is 1 plus a k squared over 2. Second condition is f prime of 0 is equal to 0. F prime of 0 is 0, so I get 0 equals 0. This is not very useful. So in fact, I didn't really find the good boundary conditions by looking at the first derivative. This is because of the particular shape of the solution. We don't have 2 independent boundary conditions. It's very specific. In fact, we need 1 more because the first derivative doesn't help at all. So the next order is the second derivative. So we can deal with the second derivative. Let's take the alpha of f. The alpha, if f is provided by this, well, the alpha of f is a k alpha. And if I repeat the process by deriving once more with respect to alpha, I get a. This is a function of k. But it's equal to a constant. So I can always evaluate it at k equals 0 if I wish. So this is also true. But what is nice is that this quantity is connected to the second moment of the distribution of the vector S. Remember the relation between the characteristic function and the different moments. And this is, if you remember the good step, was calculated, I guess, here. Here, the second derivative with respect to alpha and beta is the correlator between S alpha and S beta, but now I have the same alpha and beta. So this is minus S alpha squared taken in the uniform ensemble averaging. All right? And then to conclude the problem here, I need to know that guy. Well, remember that S squared is equal to N. It is also the summation over alphas of this. So I can really take the average of that and say that the average of N is equal to the sum over alphas of the average of S alpha squared taken in the 0 sense. Well, of course, this is equal to N because N is a constant integer. And it's an isotropic distribution, so we could really calculate everything, but we know that all the directions are equivalent here. So it's N times the same. Let's call it S1, for instance. Could be S2, S3 until Sn, whatever component, but it N times the same thing. All right, so it tells me that you have N here and N here. Basically, we know that S alpha, whatever alpha is equal to 1. Right, so one component is normalized to 1. That is why the sum of N components squared will be normalized to N. This was the normalization choice by De Gennes. Therefore, if I remind you the final relation we had, this is equal to -1. So we end up by finding A. And so if we find A, we can finish our expression of F, and we found -1 K squared over 2. This is equal to F. So this is the final result. We found the characteristic function of a uniformly distributed spin that has 0 component. All right, so we have solved the problem in the Fourier space, if you wish. Let us comment on that fact. Let me open a new whiteboard. It's interesting. It's a parabolic object. So what is the immediate conclusion that one could have? Would you have an idea? Remember that the characteristic function, when I derive it, I get the moments of the spin. If I derive it 0 times, I get the normalization. If I derive it once, I get the first moment, twice the second moment, so correlator between 2 components, and 3 times 3 operators, and so on and so forth. So according to the parabolic shape, what can we conclude very easily? Well, we can conclude that any moment beyond the second moment is 0. If I derive, so f of 0 is 1 by construction, the alpha f of 0, well, the alpha f is minus k alpha, okay, so it's 0. The second alpha f of 0, well, it is -1 here, as we already used. But now if I derive 3 times f, well, I derive a constant number because it's a parabolic function, so I get 0. It will be the same for any larger derivatives. So altogether, this characteristic function here tells me that no correlator involving more than 2 objects will be finite. So in a nutshell, there is only one non-zero moment, or 2 at least if I remind you that this is obviously 1, but this is a trivial one. The only one that matters, the only one moment that won't be 0 is this one. And this will be equal to 1. Anything else is 0. If I take a single quantity, it is 0. If I take S alpha, S beta, with alpha being specified to be different from beta, 0. If I take larger numbers of components, 0, 4, 5, 6, whatever. So really the problem is very simple in the sense that there is only one moment that is non-zero in this problem. It's a very easy result. Of course, this is in a dramatic limit where the number of components of your spin is 0, n equals 0. So let us not discuss too much about that for now. So you understood, we went from a Ising type of problem with different spins. We isolated one spin inside, and we assume first that we were in the infinite temperature limit, so it's completely uniformly distributed, this spin, all right? For that problem, we solved it. We found the Fourier transform of the distribution under all the moments, and we realized that in a very specified limit, n equals 0, we end up with only one specific moment, the correlator, the self-correlator, to be non-zero. All the rest is 0, so it will simplify a lot the calculations. All right, so far, those are only mathematical tools and reminders of statistical physics of an Ising type of problem. Okay, I hope you're all with me. And now we will slowly move towards soft matter and polymer physics. We have all the tools to attack now the main calculation one wants to perform in StatPhys, which is to find the partition function. So now we are not saying that T is infinite. Now we are going to a finite temperature. So the zero averaging the uniform distribution doesn't apply anymore. We need to go to the Boltzmann distribution with the exponential factor and temperature inside. Okay, so the results are different when now the temperature becomes finite. But we will use the connection we made between the canonical average when there is a temperature and the uniform average when the temperature is infinite. And we have a formula between the two, so we will invoke the uniform result to get results for the canonical problem. I hope you are all with me now. All right, so let's calculate, or at least re-express the partition function. If we come back to the very beginning of the tutorial, we wrote the following formula. It's here, the partition function normalized by the total solid angle of the problem. Now I have again all my spins. I'm not anymore considering one spin, but I have all the spins. Well, it's simply the zero average, so the uniform distribution here, but I have put the Boltzmann factor in the average. Okay, so I'm just averaging the Boltzmann factor with all degrees of freedom. So let me start from that. Z over omega, I just rewrite exactly the same thing. We wrote that it's Tj over the real temperature, and then you have a summation over all spins. Remember, counting pairs only once and making sure that we only count nearest neighbors. And then the two-body interactions between two spins that are nearby. And we've written the partition function in the uniform limit or in the uniform distribution. All right, so this is just a writing trick. Now we want to take the limit n goes to 0. So in that sense, this will be provided by the limit of the previous expression, and I will also express a bit more this expression. I have the exponential of a sum, so I can transform that into a product of exponentials. So I just put in front the product. Again, the bounds are exactly the same. And then we have single exponentials now over, Si, Sj, which I can also decompose into its components. So this can be rewritten this way. Nearest neighbors counted only once, and then I will specify the scalar product. So the scalar product is the sum over all the components of the product between components. Right? It's just writing. Okay, so now let me remind you that the exponential has an expansion in series for any value of the argument. Okay, the convergence radius is infinite for the exponential. So I can always formally put the exponential as an infinite sum of polynomial terms, linear, quadratic, cubic, and so on and so forth. And so this can be, and the expression starts to be a bit longer, as you will see. It will be more and more the case. I open a parenthesis. I have 1, the first term of the expansion of the exponential, then the linear term, tj over t, sum over alpha, si alpha, sj alpha, plus the quadratic term, and remember there is a factorial 2 that appears somewhere, tj over t squared this time, and then I will put the summation over alpha and beta. Now I have two sums, si alpha, sj alpha, si beta, sj beta. Then I have, and sorry for the space, I have a cubic term, so tj over t cube, and then 3 indices, gamma for instance, si alpha, sj alpha, s, sorry, s, up, undo, si beta, sj beta, si gamma, and sorry for the handwriting, j gamma, and then etc. At the end, I just close this parenthesis and again take the 0 average. So sorry for the writing. I will anyway shorten it in a minute. All right. So you see, you have an infinite series and you go to any term, any order. However, now we are in the limit where n goes to 0. So when n goes to 0, I remind you that we had the following result. Only the second order moment, so only product with two identical fields will provide a value that is non-zero. All the rest, for instance, when you have 3 terms in a row, will provide 0 at the end. So you can see here, I have this guy appears once, and we will comment it in a minute. This guy I appears here and here, and this guy I appears here, here, and here. So for sure, this type of term will be 0. No matter what you put in front, there will be at least 3 SI. So this is 0. And this is the same for all the remaining parts of the summation, because then you might have 4 SIs, 5 SIs, and so on. So in the n equals 0 limit, since the characteristic function is parabolic, we can drop all those terms in an exact fashion. This is not an approximation, a Taylor expansion stopping at the second order. No, it's an exact result. There is a truncation of the summation that is exact. So we end up with the final result, or the final expression, that z over omega, and always in the n equals 0 limit, will be provided by the summation. So first there is a product here of 3 terms. You have 1 plus tj over t times the scalar product, and plus another term, and only one, And then with no approximation, this is it. So it's of course a huge monster because here we are integrating, there is a product with I and j, so we are product factorizing all the possible terms on the lattice. However, with truncating largely this problem because now there are 3 terms in the product instead of an infinity. So it's much more simplified, and this is related to the parabolic aspect of the characteristic function. All right. So this is the stuff we want to calculate. We want to calculate the partition function of our real Ising-like problem in the canonical ensemble. Okay. So this is the real partition function, but we've expressed it with a finite number of terms and a product in the 0 sense. So we are calculating everything in a very simple world where the distribution is uniform, temperature is infinite. All right. So this is the object we want to calculate now. So this is field theory, if you wish, statistical field theory. We want to express the partition function, and we have several terms involving fields, either product between 2 fields or 4 terms. So you have interactions that are more and more complex, if you wish. So as usual in statistical physics field theory, we will invoke Feynman diagrams, meaning that we won't rewrite all the terms each time, but we will make a connection between each term and a cartoon, so that mentally it's easy to see what we are talking about. Of course, at the end, we are not summing cartoons, we are summing mathematical quantities. But this is very convenient, as you will see, and moreover, it will start to provide you the intuition that there is a strong connection between Ising-like problems and polymer physics. Okay, so let us start with the diagrammatic representation. I will attribute to each term a drawing. So let me first rewrite the previous expression, but I will go slowly and write all the terms. I mean, I will start to write all the terms. So it's a product. So let me take the first case where I equals 1 and j equals 2. I have 1 plus tj over t, sum over alphas of S1 alpha, S2 alpha. Same. Now I change to 2 terms, S1 alpha, S1 beta, S2 alpha, S2 beta. Done. Then there is another term because it's a product, and I just shift by 1 unit. So now it's 2 and 3. Tj over t, S alpha, S2 alpha, S3 alpha. Same here. S2 alpha, S2 beta, S3 alpha, S3 beta. And I could do the same with 3, 4, the same with 4, 5, until I've reached all the sites. In the thermodynamic limit, this is an infinite product. At the end, I end up by closing my average. Okay, I'm just writing this so that you see what type of monster we have to calculate.
Excuse me.
Yes, please.
I think there's a question about, because f is bounded by 1, so how can it be a parabola?
Sorry, let me come back. So you want to see the expression of f here. Here, for instance. Yes.
How can you explain the k-squared?
I mean, we demonstrated the k-squared by solving the function. So then I will come back to your question, but we solved the function describing f, which is here. We use 2 boundary conditions, at least this one and another one that we found after for the second derivative, it's here. And then from those 2 boundary conditions, we ended up with this expression. Can you reformulate the question to explain why it should be bounded by 1?
Because it's an average over something of norm 1.
Yes, and then your conclusion is that k cannot be bigger than, gets, for instance, larger than what value? I mean, it's an inverted parabola. There is a minus sign. So can you go ahead?
Yes, it's between -1 and 1. So.
Yeah, so it can be negative. That's what you are saying?
Yes.
If k becomes very large, this can become negative, right? So then this is, you are pointing to the fact that this n equal theorem is a weird thing because you are doing some inversion limit. Remember that, for instance, can I write here, k is something like k1 between 1 and n. But then you're saying something like n equals 0. So you see, there are plenty of mathematical tricks behind that are not really controlled for now. And so you might see some paradoxes, if you wish. I don't know if it answers your question.
Not really, but okay.
So indeed, I think what you have in mind is that the definition of f is something like that. So in a sense, you have in mind the fact that what is average has a certain modulus that is 1, right?
Yes.
Okay. So in a general situation where n is a finite number, it's an integer that is not equal to 0, we obtain an equation for f. And then we take the coarse limit, n goes to 0. And we don't control really that limit. But it might happen that the modulus of f is not necessarily 1 here. And so you should try to locate which step breaks the property you have in mind here.
Okay, but okay. We solved the equation by saying that n equals 0, so we got an equation that was simplified.
Yes, exact.
And then we took the value for s alpha squared using the fact that n was not equal to 0.
Exactly. So it's precisely what I was commenting just previously. We make a calculation for a finite n, and in particular, we assume, for instance, that you have this kind of property, that you have this kind of property. Many stuff are related to n, in fact, okay? But suddenly you take a very coarse limit, assuming that n goes to 0, almost in a continuous fashion, I should say, but n goes to 0. And so the question amounts to the validity of that step, right? And I told you at the beginning of the tutorial that I won't enter into mathematical details because you will see we have plenty of stuff to explain in the article of Dejean. And so I'm trying to digest you that article and provide you the main elements. We will have the final result based on many assumptions like this that are not necessarily controlled. I will also do some limit inversion in a minute that is not very controlled. And then you have the chance to look at the mathematical details later. I hope it helps a bit, all right?
Okay.
So if okay with you, we continue and then we can chat together by phone or mail.
Okay.
Okay. All right, thanks for the question. So we are now dealing with, assuming that all we wrote was correct with no mathematical problem, we end up with this very big product. And this very big product, we can first see that since it's a product of three triplets, like this one, this one, this one, and so on, well, the first obvious value is that there will be 1. If I take this, the 1 here, the 1 here, the 1 here, I will get something like the limit when n goes to 0 of, well, there will be 1. Then there might be a term where instead of taking 1, sometimes I take this, for instance. So I do 1, 1, 1, 1, 1, and suddenly I take a cross product, and then 1, 1, 1, 1 again. So sometimes you will have, for instance, Tg over T, sum alpha, S2 alpha, S2 beta, S3 beta, no, S2 beta, sorry. Up. S3 alpha, sorry. Then you might also have terms where you take 2 of them. So you take 1, 1, 1, 1, 1, then 2 cross terms, and then again 1, 1, 1. So you are seeing what type of objects we are dealing with. And now I want to provide you a schematic, diagrammatic representation of all that. So the 1, 1, 1, 1, 1 term there is no S in it. There is no field in here. So in a statistical field theory picture, I will call that the vacuum. Let me represent the term 1 or associate it with a mental drawing. That is simply the vacuum. Meaning, assume that we have a lattice which has nothing to do with the previous lattice. But here it's completely empty. Space is empty. This is the vacuum. Right. Okay, now this term, 2 alpha, 3 alpha, well, it's if I take node number 2 with charge number alpha and node number 3 with charge alpha, I have a bond between 2 and 3. So this will be called the interaction term 2, 3, provided that the charge is alpha. So now I'm transforming a mathematical object, which was this scalar product here, into a drawing. It's a bond between 2 and 3 with some charges. Let's say it's a chemical description, all right? So now I could also have terms like this one. I go from, let's say, 1, let's just change the numbering, to 2, and then from 2 to 3, and 1 is alpha, 2 is alpha, and in the second bond, you change the charges and you do that. So this will be S1 alpha, S2 alpha, S2 beta, S3 beta. Okay? Which might happen if, for instance, when I'm summing, I take S1 alpha, S2 alpha, S2 alpha, S3 alpha. But since there is a summation over alpha, one of these terms can be the beta that I wrote just here. So this triplet, a molecule with 3 monomers here, well, is another term in the calculation. Okay, so let's continue. We could also ask ourselves, what is this guy, for instance? S1 alpha, S1 beta, S2 alpha, S2 beta. Well, let me just, again, I changed the index notation, and I will start, for instance, here. This is 1. Let's assume that this is 1. I have 1 alpha, 2 alpha, and then I come back with beta. So it's beta here and beta here. So it starts to become a bit messy. But you see, now this is a double bond, like that. If you want, it's the double bond in chemistry here, okay? And it's written S1 alpha, S2 alpha, S2 beta, S1 beta. So it's really now this type of term. Okay, so you see, for any member of this very large product, I can always represent it just mentally for easiness by a drawing. But what is interesting is that we are already seeing that the drawings, they start to resemble connected paths on a lattice. And connected paths on a lattice resembles a polymer chain, if you wish. So at some point, if I have a very large number of objects, well, I have a random walk on a lattice. But this might resemble a term in an Ising-like problem. And I want to go deeper into this thinking. Okay, so now you see what types of representation I have in mind. All right, so now let me just start new blackboard here. All right. So I'm dealing with still part 3, but question number 2, I guess, 3. Having proposed a representation of all the terms, we would like to investigate what terms are important and what terms don't count. Okay, so now let me just review a few of them so that we start to build an intuition, and then we will use this intuition to calculate the partition function. All right, let's, for instance, so we know how to calculate the vacuum term. It's 1. So this is not very interesting. So let's look at already one specific term. We can take, for instance, site AI, site J. Those two and we assume that they have the same charge, for instance. Okay, this is the term I want to calculate. So this term is really related to the average of Si alpha, Sj alpha, with J and I being different sides. And if you remember what we wrote, this should be evaluated in the zeroth sense, so in the uniform ensemble. I and J sides are independent sides, so they don't talk to each other. We are in the uniform distribution, so one spin just moves and is allowed to visit all the configurations independently of what is going on inside. There is no interaction in the uniform distribution. So basically, we can separate the two, they are independent, into the product of the averages. This is the interest of working in the uniform sense and not the canonical sense, where there will be an interaction energy, and so you cannot decorrelate the two sides in the canonical ensemble. All right, but now you remember that each of those is zero, because the average of one spin component has as many chances to be negative as positive, for instance, because of the isotropy here. So those two guys, they are zero, and we end up with zero. Okay, so one bond is not very interesting. Let me review another example. Again, I have my vacuum, and I have an excitation in this vacuum, which has the following shape. So I go from 1 to 2, then from 2 to 3, then from 3 to 4. This guy, and let's assume that everyone has the same charge, okay? So it's S1 alpha, S2 alpha, S2 alpha, S3 alpha, S3 alpha, S4 alpha, and I will end up calculating this type of stuff, all right? There is a prefactor which is related to Tg over T. Let me remind you that in front of this big product here, at any time, you have to remember that, for instance, this term, which is average in the zero ensemble sense, well, there will be in front this guy and the summation over alpha. But now we are only, since it's a sum, there is at least, I mean, you have a series of objects, and we are looking at only one of them, and we don't consider the prefactor in front for now. All right. Okay, so let's transform that again by independence into a certain number of objects, 4. One is independent from the rest. S2 alpha squared, good news. S3 alpha squared, good news as well. S4 alpha, 0. So now, this is interesting to notice that something is different now. We know that the second moment is the one that is non-zero, thanks to the parabolic shape of the characteristic function. So this guy is 1. Coming back to the question by Krishan, I think, this has a value of 1. So the component squared is 1, despite the sum of all these should be n, which is 0, as you mentioned at some point. So you see already here there is also some inconsistency. So there is some mathematical analysis of how can you do this n goes to 0 limit, perhaps by having a continuous transformation of the problem instead of being a discrete problem. And then perhaps going closer and closer to 0, you might have some tricks to do that in a formal way. I'm doing the coarse physicist way. All right, but the good news is that the second moment is 1. So those are non-zero. That's nice. So I'm starting to identify which type of diagrams don't give 0 at the end. So that's the ones that are interesting to me. Unfortunately, you can see that we are still going to 0 because they are isolated. This guy has been visited only once. It's a starting point. Whereas this guy is visited through this bond, but also through this bond. So it appears twice. That is why it gives a non-zero result. So we start to understand the logics. If we want to have a non-zero term, we will need to have each point visited 2 times or connected to bonds in 2 directions. All right. So let's explore this idea and do another drawing. Let me consider a term that is now a closed loop, obviously. Now I start from 1 with a certain alpha charge. I go to 2 with a certain alpha charge, 3 alpha charge, and same 4. But instead of stopping there, I just come back. Okay, so now this path, this drawing, is this one. So I have first the first bond, so S2 alpha here. Then I have the second bond, so S2 alpha again, S3 alpha. Then the third bond, S3 alpha, S4 alpha. And then I close the problem by coming back to 1. I'm always averaging this in the 0 sense. Interestingly, I can group those together. So I end up with a product of 4 terms. And you see the logics now. Each of those, thanks to my characteristic function, being equal to 1. So again, a bit strange because the norm of one component is 1, but the norm of the total vector with all the components is 0 because we are in the n goes to 0 limit. This very specific choice of normalization is questionable, and I would put that question on the side. And it's related to your question before. All right, but now you see this drawing seems to be non-zero. Good. So I'm starting to say that the only diagrams that will contribute to that calculation are the closed loop. Good. So let me try to do another example. If we are dealing about loops, let's consider refinements around this idea. Here is another term. I'm just taking them at random. I start here, I go here, I go down, and then I come back. So it's a loop. Okay? And 7 and 3 is the same. And let's assume that all the nodes have an alpha charge. Well, you immediately see that I go quickly now. This will be equal to 1, 2, 3 or 7 is the same. So sorry about that. This is a power 2. Here, careful, it's a power 4. And again, there is an alpha missing. Then I have the 5 term. Then the 6. And then the 8. All right? But now, everything looks good. This is 1, this is 1. Sorry, this is 1, this is 1, this is 1, etc. But this guy has 4 times the same field. Again, the characteristic function is parabolic, so this is 0. So you see, cross loops are fine, but if they, loops are fine, but if they cross themselves, they are not fine anymore. Interesting, because a polymer, well, it's a conformation in space, but when there are interactions, if you think about a realistic molecule, it cannot come back to itself. You don't have 2 monomers that are strictly at the same position in space because there is a repulsion interaction between them, so they cannot occupy the same space. So it starts to resemble more and more a realistic polymer problem. And since I'm talking about the stat phys problem for now, I can say that the only diagrams that will contribute to the big calculation I want to perform, which is, as a reminder, written here. The first line is the short version and the second line is an explanation of all the terms. I want to calculate that, but in all that, most of the terms are 0. Okay? So when I will write the partition function, z over omega, here, it will be in the proper limit n goes to 0. The average of the product of nearest neighbors, 1 plus tj over t plus the second order term, and I should put a square. See, this is integrated over alpha and beta. Okay, so this is what I want to calculate, and I just explained you that, well, this is 1, so 1 is the vacuum. Then terms like Tg over T, sum over alpha of Si Sj. I can use colors here between I, J, and both being with a charge alpha. So this is when I take, for instance, only this term, plus terms like this one, where you have sum over alpha and beta of, it's just a representation. And then I have a double bond between I and J. So I start at alpha and I come back at beta. So I change the charge on the second part of the bond. But anyway, this has this side, this aspect. So those are situations where I take only one of them. So I take 1, 1, 1, 1, 1 everywhere, the vacuum, and then I decide to have an excitation, for instance, between this I and this J, or a double excitation between this I and this J. But this is not over, because I could have cross terms. I could take the vacuum, 1, 1, 1, 1, 1 everywhere, and then 2 bonds. So there is the situation where I take 2 bonds. For instance, this one and this one. Okay, and again, since I have 2 bonds, there will be Tj over T now squared, and then times alpha and beta, because I'm summing over. Okay, you start to see what I mean, and then I drop all the prefactors, but then you will have, of course, the closed loops, as many as you want. For instance, this drawing, I start to go far into the, okay, this is Tetris now, but also this drawing. I have the right to have 2 closed loops. They will contribute, or 2 closed loops and a line here, or a double line, say, and here a line, whatever. Okay. So you see, basically, this will be a sum of drawings, and we know that most of them are 0. This one is 0 because there is no closed loop. We want to have closed loop. If there is no closed loop, it will have a factor 0 at some point. This one is 1. We know it. It's the vacuum. This one is 0. There is no closed loop. This one might be okay because there is a loop, but we need to make sure with the alpha and betas, and so we will have a look at that later. This one is okay. It seems that this is a closed loop. This is a closed loop. Unfortunately, it's multiplied by a non-zero. By a 0 term. So this is also 0. So in a sense, the only diagrams that will matter, they are either one loop, no matter its length, or several closed loops that never intersect themselves. So I can rewrite this as the sum. Okay, so let me take the limit again here. N goes to 0. The sum of, let me call the number of bonds in one loop, n. So those are diagrams with one single closed loops. There is a certain number of diagrams with one loop. It's a function of n. And then for each of those, I will pay the price that is written here, but with the power, the number of objects. So if I have 4 bonds in a closed loop with 4 bonds, well, I have Tg over T to the power 4, because for each bond, I have to pay that amplitude. So Tg to the 4, here n equals 4. But of course, there are plenty of ways to create 4 loops. I can put it here, 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 here. So I have to count on a given lattice how many conformations or configurations of closed loop of 4 units are doable. And this is just counting. So I'm counting them. Finally, remember that there is the summation over alpha here. So I'm summing over alpha something which is equal to 1. Sum over alpha of 1 gives n. This is going like n. So you have this term. But you have other term. You have a term where I have a closed loop of 4 units here, and then a closed loop of 8 units here, or whatever. Depends on the type of lattice you are considering. But you know, I can have 2 loop excitation at the same time. I don't necessarily need to count this one plus this one. I can have a double excitation at the same time, and this is non-zero if they don't overlap. So I also need to count the loops with the diagrams with 2 loops. So this one has n unit and this one has m unit. For instance, let me show an example here. I have a diagram where I, for instance, have this one, which is a 4 unit loop. And at the same time, on the same diagram, this one. 6 unit loop, okay? Those, they count. Of course, I need to sum 4, it's not necessarily 4, it can be 6 as well, or even bigger, so I need to sum over all the possible values. And therefore, I'm putting Tg over T to the power n plus m, and I'm summing this guy for the 2 different type of loops. So I'm now summing and getting n squared, and etc. and so forth and so on. I won't continue to illustrate what you get, but you see immediately that apart from the vacuum that is remaining, so I need to add here 1 plus all that. Apart from the vacuum value, all those terms, they are either linear or polynomial with higher exponent in n. But we want to look at the n goes to 0 limit. Again, strong step. I'm inverting the limit and those infinite summations. At the thermodynamic limit, the lattice has an infinite number of sides. Am I allowed to invert the n equals 0 limit and the infinite summation on the lattice? I leave that question to you. I'm just trying to retransmit what was the intuition of Dejean with simple arguments, okay? So, this is one. Okay, good. So we did all that to find that the partition function is 1. So actually it's the rescaled partition function. So we end up by saying that z over omega is 1 in the n goes to 0 limit, provided we have the right to do the limit as we did it. This is equivalent to saying that z is the volume. Or in stat phys, you've seen that. This is the ideal gas case. The partition function of an ideal gas is the volume. Okay? So this is very boring. But it will have a strong incidence, because now when we will look at special observables and not only the partition function, the denominator of all the averages is normalized by the partition function in stat phys. But the partition function is a constant. So you will see that the expressions will be very simple. And this is what we want to do now. So this is the final part where we will connect really the problem to polymer physics. when you're dealing with statistical physics, near a critical point, you know that the correlation between fields might diverge. For instance, a spin on a lattice generally is talking to a spin nearby with a certain interaction. But at the critical point, the typical extent of the correlations becomes infinite. This is one characteristic of a critical point. Every individual object will talk to an object very far away at the opposite end of the sample. The susceptibility will diverge. The correlation lengths will diverge. This is what we just said. And so it's a very interesting object to study, namely, what happens if I consider one spin at position P with a certain charge, delta. Sorry, the delta look like S sometimes, but be careful. When it's an index, it's a delta. And Q. So in a stat phys problem, we would be really interested in knowing the correlator between two spins on the lattice. And be careful, we are not putting a zero here. It's really the canonical averaging. So it's a real stat phys problem under a certain reservoir of energy, a thermostat. There is a constant temperature on the system. This is really the main quantity we want to express. All right, let us try to use all the mathematical tricks we've presented and take the n equals 0 limit in order to see if we have a simple expression for that. So first of all, I told you at some point that if I take any observable G, the canonical average of it can be related to the uniform average. So I think the exact formula was the following one. Up. Again, summing over all the nearest neighbors, Si scalar Sj, in the zero sense, but here with the partition function at some point. All right, good. The first aspect of it is that we transformed the canonical averaging into a uniform averaging. So the spins become independent. There is no more interaction energy and so on and so forth. And also, we've calculated the characteristic function for a given spin, okay, in the n equals 0 limit precisely. Also, what we just did is to evaluate in this limit z over omega, and it is 1. In fact, this is the denominator that is here. This is z over omega, if you remember the definition, okay? So we end up in saying that basically, this is what we have to calculate, and only that. As simple as that. Okay, so you have the correlator of the Ising problem in a canonical ensemble, which is transformed into an average in the uniform ensemble. And you have two spins, and then the infinite sum that we already wrote before. So we already know the diagrammatic representation of all that. It really resembles what we did before. The only novelties are the presence of those two guys here. But basically, we will again go to diagrams now that we understand the connection and try to see which diagrams matter and which don't. And there will be differences with respect to what we had before in the absence of those two guys. Okay? So now, in the same spirit as before, we can write an exact expansion for SP of delta and SQ of delta. It is, I just write what is above, And then I have an infinite product, exactly as before. Then I have this 1 plus Tj over T times, and then the quadratic term with, as usual, alpha beta closing everything here. And my claim is that this is an exact expansion in the limit where n goes to 0. There is no more additional term. I'm not doing an approximation. The terms that contain more than 2 I symbols, here I have 1, here I have 2. If you have 3 of those, 0, thanks to the characteristic function parabola. Okay? So it's a closed problem as before. The only difference is that now I have 2 more points, and be careful, their site is fixed. There is no summation on all sides. It's a very given P and a very given Q. And also their charges are fixed and are equal here. So let us see what it means in terms of diagrams. I take my vacuum. For sure, I have at least 2 things present on that vacuum. I have the P site with a certain charge delta, and I have the Q site with the same charge. And for now, I will assume that P is different from Q. The P equal Q case being simple to calculate. You will do that. All right, I have that, and I want now to either put nothing more. This will correspond to taking this one, and then 1, 1, 1, 1, 1 everywhere. So this is exactly the drawing I made, but I can also decorate it. I can just add a closed loop somewhere. So for instance, what happens if, based on my previous intuition, well, okay, very nice, I know that loops are good, so I put loops, good. So it should not be 0, right? Okay, let's see what it is. It's SP delta, SQ delta, and then let me put deltas so that I have the feeling that having the same charge is good. Then I have S1 delta, S2 delta, S2 delta, S3 delta, S3 delta, S4 delta, which is then connected to S1 delta. I just have this type of term to calculate. Good. This one gives 1, 1, 1, this plus this 1. Unfortunately, those guys, they are isolated. This becomes proportional to SP delta in the 0 SQ delta in the 0 sense. And this is 0 because we know from the characteristic function that the first moment is 0. It's a uniform distribution. So you see, closed loops are not good anymore because we don't want to leave those guys completely isolated. So the trick is to connect them. If you connect them, you might have more than one single field. So you need to connect the start and the final point. Good. So let me then take another example. I start from here. This is P. And I end up here, which is Q. Delta and delta in terms of charge. And I will consider this path. I go to 1, and then again Q. Well, this is SP delta S1 delta. Let me assume that it is charged the same way. Then S1 delta SQ delta. And of course, in my calculation, I need to remember that in front I have SP delta and SQ delta. So I have SP delta at the beginning. I can put SQ delta at the end. Now this is good because it becomes SP delta squared, S1 delta squared, SQ delta squared, which are all equal to 1. Okay, so we identified the diagrams that contribute. They are all the passes that will connect P and Q with linear trajectories. This is really a polymer now. We have an origin, we have an end, and we have some number of monomers in between. This is the drawing of a polymer. The very interesting aspect here is that when I've written S of P and Q and delta and S of Q and delta, I've specified the charge, delta. It's not anymore an index over which you sum, it is specified. Therefore, when I will multiply it with this type of term, there are many alphas, but among this summation over alpha, there is delta. And I will only keep that. So the summation will disappear. This will be 1, but there will be no summation over delta. And remember, our problem previously was the summation over alpha that was giving something linear in n or quadratic in n. And when I take the limit n goes to 0, this is dead. This is over, it vanishes. Now we have something that doesn't vanish. So if you understand my claim, my point, let me just switch here. What we want to calculate at the end, the correlator in the spin-like problem, in the canonical ensemble, is in fact how many ways do I have when I want to connect the starting point and the final point with a chain that always has the same charge. Well, there is this drawing, but I could have decided to go somewhere else. I could have decided to go from here and then here and then here and then come back. It's another configuration. Or I can go very far away and then come back at that point. So the idea is now to count all the possible trajectories connecting the starting point and the final point. So I'm saying that, let's assume that this trajectory for now has a certain number of steps, capital N. I'm counting the number of trajectories having n monomers, so n bonds, connecting P and Q. This is a statistical or combinatorics object. I can count that in practice. For each of those polymers on the lattice, I have a certain weight. Remember here, I have this guy for each bond. So this should be put to the number of bonds in terms of power. So I have Tj over T to the number of bonds. And as I told you a minute ago, well, the number of bonds could be 2, this is the red example, or it could be larger, this is the blue example. In fact, I will sum over all possibilities, either connection with small number of bonds or larger number of bonds and all possibilities. So I need to sum over n. Let me just stress that this is the number of paths connecting P site and Q site in exactly n steps and without any crossing. We already discussed the crossing. If you have a crossing, you have more than 2 times the same field, so it will be 0. So without any crossing. And I can finally take a very special situation where Tg is equal to T. So in the statistical physics problem, I'm reaching the critical point. I go to the temperature that characterizes really my interaction, okay? So when I go to the critical point, the correlator between spin S at point P with a certain component delta is simply equal to the sum over all the possible conformation, no matter the length of that polymer. All right, and we should stop here. We are saying that an easing problem, correlator between two spins on a lattice, really hard condensed matter, is equivalent to counting the number of configurations of polymers in space. Stated differently, if I know results from hard condensed matter, because I've studied hard condensed matter and there is a huge literature about the critical points in condensed matter physics. Well, there are strategies to calculate that, whatever n is. So I can, small n, the integer that describes the number of components of that spin. So there are plenty of results giving me this quantity. But I'm telling you that it is related to the conformations of polymers. So now if I want to know the conformations of polymers, for instance, because I'm interested in the end-to-end radius, as we did last time, well, I can simply open a textbook of magnetism and just change the language, and I have my result. So I'm doing a connection between Ising-like problems and polymer statistics. It's fantastic in terms of formal description. Now you can also address other situations. What happens if now instead of having the thermodynamic limit, I'm preparing a thin polymer film? We know that a thin polymer film is really confined. So inside the chains, they cannot explore all the conformations. They have to rebound on the interfaces. So their conformations have been frozen or modified thanks to the interfaces. Well, if someone studied a finite size magnet experimentally and measured the correlation between points or the heat capacity or the susceptibility, the way it magnetizes when you put an external feed, and so on and so forth. Well, all those quantities, they can be mapped into some polymeric quantities if I understood the main result here. Finally, a very important point is this one. I wrote here without any crossings. So remember last time we were dealing with a very simplified description of polymer physics where we were assuming that the chains were constituted of monomers that were allowed to cross themselves. Really, it was freely joined. It was the Gaussian description that we discussed last time. In reality, when two monomers meet each other, there is a strong repulsion at some point, and so they cannot cross. So the crossing is forbidden for a realistic polymer chain. We call that a self-avoiding random walk. It's not a simple random walk, it's self-avoiding, it avoids itself. But therefore, here, we are really addressing this problem because we remember that the crossings will kill all the diagrammatic terms we've studied. So here it's really the number of configurations without any crossing. So we are really addressing a realistic polymer problem. All right, so I will stop here for today. I hope I've convinced you about the elegance of that connection made by Dejen. I mean, this is brilliant. Of course, you would need to digest that a lot because it's a pretty difficult topic. So revisit the tutorial. Please read the article by Tom Wheaton and also have a look at the Dejen article, despite it's very difficult to understand. And finally, as you will see, there are plenty of open questions. But since I wanted to provide you the minimal details so that you understand the idea, it's completely impossible to demonstrate all the steps. In particular, the n=0 limit, all the problems that you guys asked during the session, it's really difficult to go through that. So I leave that to mathematicians. And for you, since you want to get an intuition of polymer physics, then you have a main intuition of what is the n=0 theorem, despite I was not totally exact on all aspects. So I hope you understood it, and I hope you will have questions.
I have one.
Yes.
Is it possible to get the same result by solving the differential equation with any n?
All right, so I never tried that, and I suggest that you do that as an homework, in fact. So if you have ideas on how to do that, at least for other values of n, just to get an intuition first, that would be interesting. I never did that myself.
And then taking the n
at the end.
Yeah,
it's a good point, and perhaps it might help solving your previous question. Thanks. All right. Do you have more questions? No? So I suggest that we stop here. Please see the video again. I will upload it this afternoon, and come back with questions or comments about the interaction. I don't know if it's better or worse than last time. Of course, the topic is a bit more tricky. This won't evolve in a positive way, I guess, in the tutorials, because we will go towards more and more complex topics. But feel free to come back with questions, and I hope at least you have an intuition of something that was created today about this genius discovery by Eugene. Thanks a lot, and have a good week.